This is part 2 of the Arrhenius and rate equations section of chemistry's kinetics. In the first part we covered rate equations and the Arrhenius equation and started a past paper question. This time we're going to cover the rest of that past paper question and look at a few more examples as well. So from part 1 we were given that rate is equal to K1, the rate constant, and H plus to the order of C. Now they've plotted a concentration time graph here of H plus over time. And they want us to explain how this graph shows that the order with respect to H plus is 0. Well, if we look back at our example, we could simply just say that a concentration time graph, when it's a linear graph, it is equal to 0, or 0 order. What that actually means, though, is as the concentration is changing over time, it is linear. Therefore, the impact that concentration has on the rate is none, which is 0 order. If the concentration were to have an impact on rate, in the case of first and second order reactions as we see here, we would see a non-linear graph for the concentration time because the change in concentration will not be linear relative to time because it is affecting the rate of reaction. All we simply need to say here, though, is just to understand that we can interpret the graph. So we just simply say that the constant gradient as H plus decreases. And that's just outlining that we understand how to interpret that the concentration time graph is linear. Now, looking at part D, they want us to calculate the units of K1. And I've already done a little bit of it here. And that is, now that we know that the reaction is with respect to H plus 0, we can equate that the rate is equal to K1. And the way to find a rate of a concentration time graph is simply to find the rise over run, because we're determining the concentration per time, which is the definition of rate. So what we'll do is we can pick 2 points. I've picked these 2 points here. It's always best to pick points that are easy to read and interpret. So we'll do this over 0 minus 250, and that should give us minus 0.0012. And what are our units? Well, all we've simply done is mole per decimeter cubed over seconds. So that will be our units there. In part E, they've given us some data and they simply want us to plot this line and then potentially comment on the line of best fit. So they've given us our first 2 points here. We've got 200 and we've got 100, our first 3 points, sorry. So now we'll go to 400, 0.31 and 600, which is 0.24, and that's there. And 800, which is 0.19, and that is there. 1000, which is 0.15, and 1200, which is 0.12. Now, when you're plotting this, it's really important to have a look, because you could draw a straight line here potentially and say that that is the line of best fit. But it's really important just to look at the pattern. We can see here there's a slight curve. So for part F, the line of best fit would look something like this. And we can see there is a clear bend, and because it is only shallow, we could already make predictions and say this is likely to be a first order, but that's something you always need to determine with experimental data. When it comes to solving questions regarding the Arrhenius equation, especially in its logarithmic form, we need to go back and remember that the key piece of information here is that the gradient of this graph is equal to minus activation energy over the gas constant. So we've been given this equation, we've been given the data, and they simply want us to work out the activation energy. So we know from this that our m, which is our gradient, is equal to minus EA over R. And therefore, it's simply going to work out m by our rise or our run, which we can pick various points here, but I'm going to pick minus 14.1 minus 2.8 over 0.00180. It's really important when you're doing these questions to not miss specific figures. It's a commonplace again in these questions where you trip up. In the exam, you're rushing. Just take your time, make sure that you have got the right number of zeros in, because it can drastically affect your answer. And then this will give us minus 21,731. Now, that is equal to minus EA over R, and therefore we need to times by the gas constant. So we can say that EA equals minus 21731 times 8.314, and then we know that that value will be in joules per mole, so we then need to take that all over 1,000, and that will give us a final value of 181 kilojoules per mole. Now that was simply because they've asked for the value in kilojoules, and with the activation energy they usually always will, so make sure you divide by 1,000, make sure you check your units while you're working. In this question we've been given yet more data, but we're asked to interpret the different rate of reactions and rate law orders with regards to specific reactants. So we've been asked to show how this data can be used to deduce the rate expression for the reaction between A and B. Well, let's start off by analysing the first two reactions, and the important thing to do here is to have a look at what's constant and what has changed. So we know that here B is constant, so if we pick reactions 1 and 2, B is constant, and therefore the impact on the rate is purely to do with A. What has happened to A? Well, A has been times by 3. A has been times by 3, and the rate has gone from 2.10 times 10 to the minus 4 to 1.89 times 10 to the minus 3. Well, the rate has been times by 9, and therefore, we know that's 3 squared, therefore A is second order with respect to the reaction. Having a little look at the next part, we can analyse part 2 and 3, and if we look at 2 and 3, we've seen that there's a change in A. A has been doubled, A has been times by 2, and therefore we would expect the rate to times by 4, but the overall rate itself has only been doubled, and therefore we know that B must have a different effect. Well, what we've done to B is we've divided by 2. B is divided by 2, and that tells us that since the overall rate is simply doubled, A should be timesing it by 4, B should be dividing it by 2, and this does work out when B is first order, because we'd have times by 4 divided by 2 is overall times by 2, and that is the effect that we're seeing here. We're seeing a multiplication by 2. Therefore, first order with respect to B. So finally, we can write that the rate equation is always rate is equal to K, our rate constant, A, which is second order, and B, which is first order. And that would say that the overall respect to the reaction would be third order. Don't worry too much about the way that you word these. As far as the exam marking scheme goes, they can be quite liberal with how you write this, but generally speaking, this kind of methodology where you're simply stating the effect and relative changes in rate to concentration is a perfectly acceptable way to lay this out in the exam. In part B, they want us to use the data from experiment 4 to calculate a value for the rate constant. So we're going to start off by looking at our rate constant here, and we could swap this round. Since we're looking for K, we could say that K is equal to rate over C squared D. And then all we simply need to do is plug in these components here. So we'll pick the first reaction because that has all of the components together. So we know the initial rate is 7.2 times 10 to the minus 4 all over the concentration of C, which is 1.9 times 10 to the minus 2 squared, times by the concentration of D, which is 3.5 times 10 to the minus 2. That gives us an overall value for K of 57. Now what is K's units? Well, having a look at what we've done here, we've got mole per decimeter minus 3 seconds per second, and then we've got mole squared per decimeter to the minus 6. Minus 9, sorry, because we're squaring it. And therefore, that means that the overall units should be mole to the minus 2, dm to the 6, seconds to the minus 1, because we divide this side by this side, and we've got per seconds. And that gives us our value of the units. A few little sub-points that I just want to cover before the video finishes. Earlier on, I wrote that the units of K1, or the value of K1, sorry, was minus 0.0012. Now, it is positive, and the reason being is that in a concentration time graph, a negative slope just simply determines that we've got a decrease in concentration. And that's our interpretation of it. However, the rate of a reaction can never be negative, so we need to make sure that our answer is given as a positive value. The second point I wanted to cover is that why activation energy here is positive. Because I've got the negative of the gas constant and I've got a negative, we can simply take these two values and remove them. This shouldn't be here, and that means that our overall value of EA is positive. Again, our activation energy should be positive as well, for reasons being that if we look at an energy graph, we've got our reaction, and this here would be defined as our activation energy, we can see that it should be a positive value.